Okay, so now that we've gotten some warm up with inverse functions, we'll be able to take the derivatives of the inverse trig functions. Now, the inverse trig functions are tricky. Here I've got y equals the cosine of x drawn in red. And if I just did my trick about swapping the variables and writing x equals cosine of y, then you can see that this green curve is not a function. It fails the vertical line test. This is exactly because the cosine function itself is not one-to-one. It fails the horizontal line test. And that's going to be true of all the trig functions, because all of the trig functions are periodic. So the solution to this problem that, flipping the graph didn't give me a function, is that I'm just going to snip out a piece. Here it is in blue. And now this piece of the curve is a function. So this arc cosine function, or the inverse cosine function, is only defined for values of x between -1 and +1. And here the outputs are angle measures between pi radians and 0 radians. Now we can do these for each of the trig functions. So let's take a look at y equals sine of x. And my inverse function will be called arcsine of x. And again, we've snipped out a piece because if I flipped the entire graph, I wouldn't have a function anymore. I just take this little piece and I mirror it across the line y equals x. And that gives me, a good enough inverse function, if not technically the same as what we were talking about yesterday. Now, we still have this geometric picture of what's going on. The graphs of the inverse trig functions are still flipped from the graphs of the ordinary trig functions, just we took a pair of scissors to them after we were done. So the same insight about, well, hey, I should be able to calculate the derivative of one of these inverse trig functions by looking at the derivative of the original function instead, that still works. So let's take a look at it. So your book uses this sine to the -1 notation. I am not very much a fan of it because it looks like division, and that's not what it is. So here, because sine is the name of a function, sine with a superscript of -1 means to take the inverse of the sine function. So inverse in terms of functions, which is different from inverse in terms of reciprocals and fractions. It's not very consistent with the way that we write sine squared of x to mean take the sine function and then square it, but that is the notation that we are stuck with. So do be aware that anytime you see a trig function with a superscript of a -1, that does not mean division. That means one of these inverse trig functions. So what we're going to do is, because this is an inverse function, y equals sine inverse of x, or if you prefer, y equals arcsine of x. Why, that's going to mean that sine of y equals x, because that's how inverse functions work. They just swap the variables. Now, the arcsine function only takes values between -π/2 and π/2. So that's going to be a handy thing to remember here. And we're just going to do an implicit derivative on both sides of this equation. On the left-hand side, that tells me that cosine of y times dy on dx is equal to d dx applied to x. Oh, that's just 1. Yes. So I want dy on dx by itself. So I'll just divide by the cosine function there. And we know that dy on dx is equal to 1 divided by the cosine of y. Oh, well, I need to change this back into x variables. I definitely want my derivative to be a formula in terms of the independent variable x. So what we're going to do here is we're going to use a trig identity. I know that cosine squared of y would be equal to 1 minus sine squared of y. So I can take a square root. And that means that cosine of y has to be plus or minus the square root of 1 minus sine squared of y. And since we are working under the assumption that y is between negative pi on 2 and pi on 2, that means I don't need a minus sign here because my cosine function is positive. So in this region, cosine of y is equal to the square root of 1 minus sine squared of y. And sine squared of y is just going to be x squared, right? Because way up at the top here, sine of y equals x. Putting all of this together gives me a formula for the derivative of the inverse sine function. So if y equals sine inverse of x, or arc sine of x if you prefer, then the derivative of that function is going to be 1 divided by the square root of 1 minus x squared. So this becomes a very useful formula if you are modeling things using the trig functions. You'll want to be able to invert those functions. And then anytime we have a function in calculus, we want to know its derivative. The derivatives is one of the best ways to understand a function. That's sort of the calculus mindset. Now, we'll also want derivatives for the other inverse trig functions. So for example, if we had y equals the arc tangent of x, we can do the very same trick. I'll just swap the variables and do an implicit derivative. And that tells me that dy on dx has to be 1 divided by secant squared of y. And this one is much easier to solve because secant squared of y is always equal to 1 plus tangent squared of y. And, well, tangent of y is equal to x. That's what I said at the very beginning of this calculation. So here is the formula for the derivative of the inverse tangent function. It's just 1 on 1 plus x squared. So let's actually work this into a problem. Let's say that y equals 1 divided by arc sine of x. Is one of these problems. And, oh, there's another one, f of x equals x times the arctangent of the square root of x. Well, that first one, if y equals 1 divided by arc sine of x, and I am saying arc sine of x, for the fact that this superscript here does not mean reciprocal, it means inverse function. And oh my goodness, they just had to make a mess of everything. So we are calculating this derivative using the chain rule. My outside function is division, right? 1 divided by the arcsine function. So they've written this here using the power rule, and that's fine. It just requires a lot of mental effort, where I have 2 different superscripts that look exactly the same, The one of them means inverse function and the other of them means reciprocal. Context is important. So I can do my chain rule. The derivative of the outside function says I've got -1, and I've got to take the arcsine function to the power -2 because of the power rule. And then what pops out when I use the chain rule but the derivative of the arcsine of x, which I already know is 1 divided by the square root of 1 minus x squared. Okay, well, cool. That derivative is calculated. How do I know I've finished calculating this derivative? I've got no more d on dx's in my formula. I can say dy on dx is equal to this formula. There it is. That's the derivative. Let's calculate this other one. What is the derivative of x times the arctangent of the square root of x? So here they're playing ball. They're playing my game. They're using the arctangent notation. Well, this is going to be a product rule, first of all. Right? I've got the product of two different functions. The first of them is x. The second of them is arctangent of the square root of x. So what is the derivative of that? X times the derivative of that arctangent function. Okay, we'll get back to that. Plus the derivative of x, which is just 1 times the arctangent function itself. So this bit right here, arctangent of the square root of x, we get that pretty much for free. This piece right here might be a little bit less obvious what happened. What's going on there is that we're using the chain rule again, because my arctangent of the square root of x, I can think of as do the square root of x first. That's my inside function. And then whatever output I get, I'm going to do the arctangent function to that output. So arctangent is the outside function. My derivative of the arctangent function is 1 divided by 1 plus the square of the input, which here is the square root of x. And then I need to multiply by the derivative of the square root of x, which hopefully at this point we're comfortable saying that is 1/2 of x to the -1/2 power. So I'm going to multiply these things together and clean it up. Let's say x times x to the -1/2 is x to the +1/2. That'll be my numerator. And I'll move that 2 down to the denominator, and I'll have 2 times 1 plus x, my denominator. And then this is all plus arctangent of the square root of x. So I'm going to stop here with a table for the derivatives of all of the inverse trig functions. So there are 6 trigonometric functions. Each one of them has an inverse, which gives us 6 inverse trig functions. And here are the derivatives of all of them. So all of these formulas come from the very same idea. They are all inverse functions. So each of them I can calculate using the implicit differentiation trick. But that would make for a very long and tedious lecture, so I'm skipping straight to here are the formulas. The first column here is probably the more useful one. Derivatives for the arcsine function, the arccosine function, and the arctangent function. And then it's much less common to see the arccosecant function, the arcsecant function, the arccotangent function. They exist, and their derivatives are here in this table, but they don't come up nearly as often unless you're in some kind of niche application, at least in my experience. So what do we get out of all this? Well, once again, something that we learned a while ago, if we think about it hard enough, teaches us new derivative rules. So now there are more functions we can take derivatives of, which means more functions we can understand. I'll catch you later. Catch you later.